All right. Thanks, Phil, for the introduction, for a beautiful talk to start the session. And also, obviously, thanks to the organizers for putting together this workshop. I think this has really been a really amazing experience for me, not only to learn about sort of the societal significance and the bright future of electrochemistry, but also really to be exposed to the sort of this really diverse different areas of electrochemistry that I, as an organic chemist, hasn't really sort of fully embraced yet, which I think is a really exciting learning experience for me. So as Phil briefly mentioned, so I'm an organic chemist, or organic chemistry lab. And so when we started at Cornell about 3.5 years ago, we became really excited about this idea of using electrochemistry as a tool to innovate organic synthesis. Now, so this area of electrosynthesis is definitely not new. Actually, Professor Faulkner just talked about this earlier. Turns out the use of electrosynthesis can be traced back to a couple centuries ago when electrochemistry was actually used as a tool for the discovery and isolation of some of these sort of chemical elements in their elemental zero-valent forms. And Professor Jaramillo talked about earlier this morning that it turns out that even today, some of these really sort of potent elements are still isolated or still produced on a very large scale globally, sort of in the sort of chemical industry. Now, sort of fast forward to a few decades ago, as Phil briefly mentioned, electrochemistry has also started to be picked up by organic chemists, first in the chemical industry. Is actually used for the production of fine chemicals in also, again, on very large plant scale. You can see some of these molecules, this morale that Phil briefly mentioned. These are not only important to chemistry, to chemical synthesis, but also very important to our daily life. I would say probably in the past about 3 to 4 decades, electrochemistry, this sort of as a technology, started to sort of slowly penetrate into this mainstream of organic synthesis community. And especially in the past 3 to 4 years, I think it's really exciting to see that synthetic electrochemistry is seeing this very, very sort of exciting resurgence, and it's gaining a lot of traction in this area of organic synthesis. So in my sort of personal opinion, I think electrochemistry is becoming popular again, not only because it's a cool technology, it's potentially green and sustainable, but also electrochemistry has a number of really interesting, unique properties that will allow it to become a really attractive technology for the discovery of new reactions, for sort of a generation of reactive intermediates, as well as for sort of a promotion of bond-forming reactions that can be rather challenging to traditional chemical methods, or sometimes even impossible. Now, I'm just showing you sort of a number of examples of where electrochemistry is actually elegantly used for key bond-forming reactions in the total synthesis of bioactive natural products. And a couple of these examples are actually from the labs of the other two presenters of the session, from Phil's and Kevin's labs. Now, so when we started a few years ago in this area, we wanted to sort of build our research program around a very simple central idea, which is to combine electrochemistry with small molecule catalysis. Now, the reason we want to achieve this sort of a homogeneous electrocatalysis for reaction discovery is because we want to harness some of electrochemistry's unique capabilities that are not directly accessible using chemical methods. These include sort of the precise control over the potential input on electric surface, this ability of directly generating highly reactive intermediates via clean electron transfer events, the possibility of integrating multiple redox events in the same reaction system, and the ability to sort of externally controlling the reaction while it proceeds. Now, in addition to these attractive features of electrochemistry, we also want to introduce this element of catalysis, small molecule catalysis, not only to sort of promote reaction kinetics to make the reaction happen at lower overpotential, but also to really sort of gain control over the reaction selectivity, especially the selectivity of the steps after electron transfer. And so these selectivity factors, such as chemo, regio, and stereoselectivities, and these are very important when it comes to large molecule sort of complex target synthesis for synthetic as well as for medicinal applications. So I would like to mention that, as you've heard a little bit this morning, this approach of homogeneous electrocatalysis has actually been extensively studied in the context of energy catalysis, and very sort of creative small molecule catalysts have been developed for reactions such as water splitting and CO2 reduction. However, at the time when we started our research program, a number of years ago, the systematic use of electrocatalysis in organic synthesis was still a largely underexplored arena. So today, in the next about, 20 to 25 minutes or so, I'd like to share with you a story that sort of unfolded in the lab over the past few years on electrochemical alkene azidation reactions. And so this trilogy starts with our initial discovery of a manganese-catalyzed electrochemical diazidation reaction. And this is followed by a very detailed mechanistic study of this reaction, which uncovered a very interesting sort of charge transfer complex as key reaction intermediates. And then the mechanistic insights of this study allowed us to discover a second-generation alkene diazidation reaction under metal-free conditions. Now, hopefully, by this story, I really want to sort of show you the synergy between electrochemistry and organic synthesis, where we utilize the sort of fundamental organic chemistry knowledge to guide the discovery of new catalysts for electrosynthesis, but also electrochemistry allowed us to not only discover new reactions, but also gain deeper and better understanding of these organic reaction mechanisms. The reason why we became interested in these azidation reactions is turns out because organic azides are very important synthetic intermediates in both organic chemistry as well as in chemical biology. And particularly, this type of 1,2-diazides are interesting synthetic intermediate because you can actually convert them very easily to the corresponding 1,2-diamine or vicinal diamines. And these turns out to be very important or very prevalent structures in both bioactive compounds, as shown on the left, as well as in this family of sort of classic catalysts and ligands that are really important for stereoselective synthesis in organic chemistry. Now, the time when we sort of started on this project, I think there are some really nice ways of sort of converting specific types of alkenes, such as dienes and styrenes, into the corresponding 1,2-dinitrogenated compounds. But there wasn't sort of really a unified approach where you can essentially take any type of alkene and convert it to the 1,2-dinitrogenated compounds. So when we decided to sort of take a look at this reaction, we decided to sort of achieve an electrochemical alkene diazidation reaction and then sort of combine this with the well-known methods such as catalytic hydrogenation to form the 1,2-diamines. Now, in order to achieve this reaction electrochemically, this is our sort of a general design principle, and we hope to use electrochemically generated radical species to power this reaction. Now, specifically, we want to take an abundant azide source, azide salt, to do a single electron oxidation to the corresponding azidyl radical on the anode, and this azide would then add across the alkene to form the first CN bond with the adjacent carbon center radical. And so we know this carbon center radical, this key intermediate here, is a transient radical, is highly reactive. It can actually undergo a variety of site reactions such as dimerization, overoxidation, and polymerization reactions. So our objective became to try and find out a reaction condition that can selectively promote this radical cross-coupling reaction to install a second azidyl group onto the alkene. So in the initial stage of our reaction discovery, we did some control experiments, and we realized that indeed we can actually form this key carbon center radical intermediate via electrochemistry. So the idea here, the experiment here we did is we electrolyzed a mixture of alkene, sodium azide, and tempo as a radical trap, and we were able to actually isolate this azidyl oxygenated product in pretty high yield. And this actually results from the radical trapping of this key reaction intermediate. So this is really exciting to us, but what we also realized is that if we actually remove tempo from the reaction in the presence of just the alkene and sodium azide without any catalyst or additive, this reaction simply does not happen and cannot isolate the diazide as the major product. And it turns out if you look into literature, this activity has been documented a few decades ago by Hans Schäfer, and he reported that using direct electrolysis methods, it's really hard to diazidate alkenes. And turns out he actually had to use, and I say the reason for that is because these two radical intermediates that you want to cross-couple, they're both transient radical species. They have very short lifetime and very low solution concentration. So statistically, it's very hard to couple them in the same reaction system. So what Hans Schäfer did is that he was able to apply a very high potential, anodic potential, very high current density, and because this will actually allow him to sort of build a relatively high concentration of these radical species within this diffusion layer, and he was able to isolate the diazide, but again, still in very, very low yields, and the selectivity is also very poor. So now, in order to achieve the second C bond formation step to access these diazide products, we then decided to take a look or take a new strategy or sort of take advantage of the power of electrocatalysis. So our goal is to find a redox-active catalyst that can actually bind to the azide to form this persistent radical, which is much more stable, has a much higher solution concentration, but still maintains this sort of radical character toward addition to the radical intermediate. And ideally, this metal species, this catalyst species, can also be turned over on the anode via oxidation events. So with this idea in mind, we were encouraged by some recent literature showing actually some transition metal complexes such as this manganese and copper. They can actually form stable metal azide complexes, and they can effect the azidyl transfer to carbon center radicals that have structures analogous to this key intermediate one. So this is really encouraging to us. When we then went ahead and surveyed a number of transition metal catalysts to promote this reaction. And just to cut the long story short, this is our sort of final conditions. Under these conditions, actually just with a simple manganese, commercially available manganese catalyst, using sodium azide as the azide source, we're able to isolate this 1,2-diazide with very high reactivity. Now, talk a little bit about, so when we do electrosynthesis in the lab, we actually don't use potential stats because we want to improve sort of the throughput for reaction screening. And so what we do is actually we use a two-electrode system with a cathode and anode, and we use a power supply to control the potential between the cathode and anode. So in this case, we control the voltage to about 2.3 volts, which corresponds to about 500 millivolts anodic potential versus ferrocene. Now, so here are some of the reaction vessels we use for these reactions. I'm glad that I think Deborah asked about sort of electrosynthesis versus just traditional chemical synthesis. It turns out they're actually very similar. So this is our original sort of setup where you use a pressure tube and then you just sort of homemade make this device, and you can control sort of, again, a two-electrode system and hook up electrodes to the power supply and run the reaction. And once the reaction is done, you just do a simple column, aqueous ware coupling column, and isolate your product. So I'll show you in a minute that we can also run the reaction on a very large scale. You can just use a common reaction flask and just by sticking electrodes into the septa, and you can run the reaction. Now, recently, as Phil mentioned, there's some really nice sort of standardized electrochemical reactors that have been developed, such as this Electrosyn, as well as I think this is developed by Ziggy Waldvogel in Germany. I think the development of these standardized devices has really sort of promoted the adaptation of electrochemistry by the pharmaceutical industry. Now I'll just briefly show you the reaction scope. The reason why I want to show this is because I mentioned earlier that when we started on this project, there wasn't sort of a unified approach where you can essentially take any alkene and convert it to the diamine or diazides. And so it turns out our reaction actually is a very general approach. It's because radical addition reactions are generally pretty insensitive to the structure of the alkene substrates. As you can see here, you don't have to read through this, but really I just want to show you essentially I would say probably about 90% of alkenes we've tried can be diazided with very high efficiency with different substitution patterns and different electronic properties. So what's neat about electrochemistry is that so you can precisely control the potential input. And so we know this diazidation reaction is an oxidation reaction, and can some sort of different functionalities that are sensitive to oxidation, to chemical oxidation reactions, can actually be well tolerated in these electrochemical conditions. And this is because we can just apply enough anodic potential to achieve the catalyst turnover. And for this reason, we can actually tolerate things like alcohols, aldehydes, and amines and sulfides, and some of these heterocycles are well compatible in our reaction system. We also tested a number of functionalities that can potentially be sort of substituted by azide through nucleophilic addition, and these are also really good substrates in our reaction system. So one thing about these diazide intermediates is some of you might have realized, especially if you're from the naval labs, is they have very high nitrogen contents and sometimes can be unsafe to handle. And so we wanted to also develop a new approach that we can directly access these amines. And it turns out these azides are interesting, but for synthetic or for medicinal applications, really it's the diamine, the vicinal diamines that you want to isolate. And so we're hoping to be able to develop sort of a tandem approach where you can do electrochemical diazidation and directly subject the reactive intermediate here into the next step, potentially catalytic hydrogenation reaction, without having to elaborately isolate this in synthetic intermediates. And turns out this actually, through some optimization, this actually works really well. As you can see, we can still synthesize these diamines in a sort of two operations in pretty high yield with pretty high functional group compatibility. And turns out now, these days, we actually use this diazidation, this tandem procedure routinely in our lab for the synthesis of diamines for other projects going on in the lab. Now, for example, this diamine here derived from a tetrasubstituted alkene. Turns out this actually is a really useful diamine for making, for instance, these sort of covalent ligands. However, the diamine is actually relatively expensive. And so the traditional way of making this is to start with a 1,2-dinitro compounds where you use a super stoichiometric amount of tin as the reductant under very harsh conditions. This reaction is very hard to scale, but also is very hard to work up the reaction because the byproducts you generate from the reaction. So it turns out we can actually use our electrochemical tandem reduction process to achieve the synthesis of this reaction with very high, essentially quantitative yield at least 100 millimole scale to isolate about 20 grams of amine, which is sufficient for our applications in other organic synthesis projects. So I'll tell you a little bit about the mechanism of this reaction. So this is still an ongoing project, but we did do some cyclic voltammetry as well as UV-vis studies to show that this reaction is actually mediated by a manganese 2,3 catalytic cycle here. In this process, electrochemistry is used to turn over the catalyst to generate this reactive manganese 3 azide species. And this manganese 3 azide is essentially sort of a reservoir for azidyl radical. It's stable enough, but it's also reactive enough to deliver the azide to the alkene in a stepwise fashion. Now, we think in the first step, this azidyl delivery to the alkene is actually outer sphere mechanism where there's no coordination between the alkene and the manganese center. And this is also true for the second step, where manganese, the same catalytic species, delivers the second azide to the carbon center radical here. Now, as I mentioned, this is still an ongoing project in the lab to understand the mechanism of the reaction. But I want to mention this mechanism because it's actually relevant to what I'm going to talk about later, a couple other projects I'm going to discuss. Now, sort of the second story in this trilogy is alkene azidyl oxygenation reaction. And this is actually a control experiment we did during the discovery of the diazidation reaction. So essentially, let me just remind you, so if you electrolyze a mixture of alkene, sodium azide, and tempo as a radical trap, you can actually get this azidyl oxygenated product in pretty high efficiency. The mechanism is relatively intuitive, right? So you generate azidyl radical, adds to the alkene, and trap this radical with tempo to give you the desired product. However, when we sort of studied the rest of this reaction, one question we had about the mechanism is how can we actually generate this azidyl radical in the first place from sodium azide? Perhaps the most intuitive mechanism that you can envision is you can just do a direct anodic oxidation of the azide anion to the corresponding azidyl radical, and that can indeed happen based on cyclic voltammetry with a potential of about 500 millivolts versus ferrocene, as shown by this irreversible black trace here. But the issue here is that if you look at the reaction system, you also have tempo in the same reaction system. It's actually much easier to oxidize tempo at around 250 millivolts here, as shown by this really nice reversible curve. And so what this means is that we actually don't have to invoke this direct azide oxidation process. And an alternative pathway would be that turns out that your azide can also be, the azide oxidation can also be mediated by this tempo and tempo plus redox couple. Now, so it's actually pretty relatively easy to distinguish between these two mechanisms. And so what we did is we did electrolysis under control potential conditions. We hold the potential to about 300 millivolts between the oxidation peaks of these two species, and we still isolate the product in very high yield, which tells us that most likely it's the pathway 2 that's the predominant pathway leading to azide oxidation to azidyl radical. Now, this is really fascinating process, right? So based on this potential difference here, it's possible that this reaction goes through a direct electron transfer in outer sphere fashion, but more likely it's probably going through an inner sphere transfer process because it's an uphill process. And so we want to really sort of try and study this mechanism of this particular elementary step in depth. And so the way we study this reaction is actually we employed a wide variety of different techniques, including spectroscopy, cyclic voltammetry, and kinetic analysis. And so what we discovered is something that's really, really fascinating here. So it turns out if you electrochemically oxidize tempo to tempo plus this oxoammonium ion, if you treat this with azide anion, you actually form this very sort of a pretty color, this dark orange color complex. And this complex can be detected by UV-vis with the sort of a wave or the sort of the sort of wavelength at about 380 nanometers. And this is different from both tempo and tempo plus. So this complex is actually semi-stable, so it's stable enough to be analyzed, but it does decompose slowly with a half-life of about 7 minutes, reverting back to tempo radical and presumably nitrogen gas from azidyl radical dimerization reaction. So we can actually also detect the formation of this charge transfer complex by cyclic voltammetry. So essentially, I've shown you the CV data for this tempo and azidyl radical, or azide to azidyl radical. If you mix azide with tempo and do another CV, you actually see a catalytic shift of the tempo oxidation wave here. And this shift actually follows, if you do a sort of a concentration-dependent experiment, it follows the Nernstian dependence. And if you plot the peak concentration of this tempo oxidation as a function of log azide concentration, you get a linear correlation with a slope of about 58 millivolts per decade. And what this tells us is that this binding event is reversible and also has a stoichiometry of 1-to-1. So this is really exciting to us, and we decided to try and figure out what kind of complex we're actually forming in this reaction system. So as I mentioned, at the early stage, this is about a year ago, it was difficult for us to isolate the compound because it's actually a semi-stable species. So I actually resort to computational analysis with the help of my colleague Kyle Lancaster, and we're able to figure out actually, at least computationally, the most energetically viable structure is this structure shown here, where you have an azide essentially sort of forming two bonds with the endo motif of the oxoammonium ion. But if you look at the structure more closely here, the azide species is only sort of slightly bent, it's about 170 degrees, and you have this relatively long bonds, and endo distances are about 2.5 angstroms. So this is definitely not a covalent adduct, it's more of a charge transfer complex. And really excitingly, actually, just a couple of weeks ago, we have been able to actually first time obtain a crystal structure of this complex here in collaboration with Hosea Nielsen at UCLA. And we actually showed that this computational predicted structure is actually the real structure, at least in the ground state, in the solid phase. And that's something we're really excited about because the way I see this, essentially, you're sort of using a different dichlorophyll to capture essentially the transition state of a 3+2 cycloaddition reaction, which is something we're really excited about. We're going to try and study the mechanism more in the future. Now, I'll just show you through a number of kinetic analysis, we were eventually able to figure out the reaction mechanism. So the way how the reaction works is that you electrochemically generate the tempo plus, and this reacts with azide to form the charge transfer complex that I just told you about. The charge transfer complex is actually the most stable state, is the resting state of the tempo, and this can then undergo sort of uphill homolysis to give you tempo and azidyl radical, and this is followed by relimiting addition of the azide to the alkene, and then sort of a follow-up tempo trapping of the carbon center radical to give you the product. I would say it's a straightforward mechanism, and I was really excited to see this, to be able to figure out what's going on in the reaction flask. But we're also even more interested in trying to figure out if we can actually utilize these mechanistic insights to help us discover new reactions or new reactivities. And the idea we had here is, can we actually turn this tempo-consuming azidyl oxygenation reaction into a tempo-catalyzed electrochemical reaction? Okay? And so the idea here is, if we want to turn tempo into a catalyst, we have to trap this carbon radical with something else. And we're actually inspired by some of our early work I just talked about this manganese-catalyzed diazidation reaction, where this manganese-3 azide species essentially serves as a latent azidyl radical to deliver the azide to the carbon radical here to give you a second C-in bond. So we're thinking, can we actually utilize this tempo azide complex, which is shown here again, to behave essentially in the same way as this manganese azide, to also do this azidyl radical group transfer reaction? Now, what we thought, I guess at the point, sort of naively, is that, tempo is really interesting as a special organic molecule because it's actually very similar to a transition metal. It has 3 continuous oxidation states. So maybe it can actually behave as a transition metal in this radical reaction. Now, so if this can indeed happen, what we can get is actually you can trap this radical again with the azide to form this diazide. At the same time, you can liberate tempo for another round of electrocatalysis, electrochemical oxidation to turn over the catalyst. Now, I'm happy to report to you that this reaction design indeed works really well eventually after rounds of optimization efforts. I can tell you, I'll be honest with you, the discovery of the reaction was purely serendipitous, but the design principle that I mentioned on the last slide really guided us to optimize this reaction. So I'll show you, so again, electrochemical diazidation reaction, now using a catalyst that's structurally very similar to tempo. We call this CHAMPO. This is from cyclohexane-derived acetamidal piperidine oxide. And similar to TEMPO, we did some modification to the catalyst. So we think this acetamidal group at the 4 position, for reasons we don't understand yet, can actually stabilize the oxidized oxoammonium form of this catalyst. And this bulky cyclohexane groups is because if we do this reaction with just simply with TEMPO, we always get this TEMPO trapping product as a byproduct, and this will just simply kill your TEMPO catalyst. We think if we can actually bulk up the catalyst, we can actually prevent this radical dimerization, or I guess cross-coupling from happening. And so under these optimal conditions, now we can do the alkene diazidation reaction under metal-free conditions now without even any manganese catalyst. And we can actually utilize, in this case, because we use water as the co-solvent, because sodium azide is soluble in water, we actually don't have to add an exogenous electrolyte, lithium perchlorate in this case, and just run the reaction with sodium azide as the sole electrolyte. I won't talk too much about the reaction scope, but I do want to mention this reaction is similar in terms of scope, similar to the manganese diazidation, where it's applicable to a wide variety of different alkenes with different sort of substitution patterns and electronic properties, which is something we're also very excited about. Now, I think my time is almost up, so after the initial discovery of this alkene diazidation reaction, we have been able to show in the past couple of years that this electrocatalysis approach, by combining electrochemistry with homogeneous catalysis, it turns out to be a very general approach for the alkene difunctionalization reactions to synthesize a large variety of different molecules to form carbon-carbon, carbon-hetero atom bonds. And recently, we have also been able to make some of these molecules enantiomer selectively by doing asymmetric electrocatalysis. I think that's something that I think we're very excited about. It's something that even though we're doing sort of fundamental chemistry, this is where we can actually sort of connect to sort of medicinal chemistry, the medicinal chemistry world. Now, I want to show you to conclude this presentation, because part of the title of this workshop is societal needs, right? Meeting societal needs. I do want to show you this sort of CNN article that was published a couple of weeks ago. I think Phil briefly mentioned in his presentation as well. As I mentioned, so we're mostly in our lab, we're doing fundamental chemistry. We're interested in discovering new reactions and uncovering new mechanism. However, it turns out some of these sort of fundamental research in our lab, in many other labs, many of the speakers here, have very important revelations in the real world, right? So I think in the past few years, because of the new reactions we developed, because of the new devices that people have discovered, we have been able to sort of introduce or promote electrochemistry to the pharmaceutical industry, which is something that's really, really exciting. I think we're only starting to sort of scratch the surface. I think electrochemistry has tremendous potential in this case for us to discover new reactions and making new molecules that are important to the society. And so with that, I want to conclude my presentation today, and this is the most important slide. I want to thank this sort of group of really talented and dedicated students who made all the chemistry possible that I just talked about today. And I want to point out a couple of people who are, I guess the slides are a little bit, the screen is a little bit small here, but so Nian-Kai Fu, a former postdoc, is the person who discovered the diazidation reaction, and he's really sort of spearheaded all of the sort of many of these difunctionalization reactions that I talk about toward the end of the presentation. And the graduate student, Juno Xu, is the person who studied the mechanism of the reaction in detail, as well as developed the second generation of the diazidation reaction in collaboration with Joe, as well as a couple of undergraduate students in the lab. Finally, I want to thank you for your kind attention, for the opportunity to speak at this workshop. I'm really happy to attend the rest of the workshop, but also to answer any questions you may have for my presentation. So thank you very much.
Thanks, Sung. That was spectacular. We'll open the floor to questions.
So the second step, the mechanism you proposed for the diazidation, the second step. So obviously you have a carbon-centered radical, and you said it's the carbon-centered radical directly couples with N3 radical instead of coupling with magnesium and then reductive elimination. Do you have any experimental evidence for that?
Yeah, so you're talking about the manganese or the TEMPO?
Manganese.
Manganese, okay. So We don't have yet any sort of experimental. We're doing some kinetic isotope effects to study the mechanism. But based on computation, the reaction actually go through two sort of other sphere like group transfer steps. So basically, you don't have a coordination of your alkene with manganese. So we've thought about sort of alkene addition to the manganese to do essentially migratory insertion, and then you reductive eliminate to form the CN bond. Actually, that's actually energetically very costly. So we think that's actually just a direct azidyl transfer to the alkene. Okay. So same goes with I think you asked about the second step as well. So there's no reductive elimination. It's actually just an outer sphere electron transfer, which I think is a really important question because one thing we've been trying to do for a long time is to make these reactions into selective by using a chiral manganese complex, and it's been really difficult because of this outer sphere group transfer mechanism. So
thank you.
Thanks.
Other questions? I don't know if I asked you a long time ago, Sung, but can you conceive, and this it may be very difficult, but can you conceive of a way that one could maybe through a paired electrolysis get the azides to reduce in the same pot, or that's just, that's outside the window of what's possible?
No, that's a great question. We've thought about it for sure. So the idea is you can generate azide and then reduce it directly on the cathode, right? You can get the diamine in a single pot. So the platinum catalyst, the surface area is not large enough. Okay. If you get you can use platinum mesh, which becomes much more expensive. So we're thinking about maybe using because the hydrogenation we actually use palladium on carbon. So maybe using palladium electrode we'll be able to do that. But yeah, that's a great question. We definitely hope we can actually do that. Thanks, Phil.
All right, let's thank Sung again for an awesome lecture.